In today's class, we will discuss about the sequence impedances and sequence networks of transmission lines. So, any transposed transmission line is symmetrical. Okay. So, in the case of positive and negative sequence currents or voltages, the phase angle between them will be 120 degrees. Okay. So, IA1, IB1, IC1 are the positive sequence currents. They mutually differ by 120 degree phase angle. In the same way, negative sequence currents IA2, IB2, IC2 also differ mutually from each other by 120 degree. So when you add IA1, IB1, IC1, you will get a 0. Similarly, IA2 plus IB2 plus IC2 will also be equal to 0. Okay. So that means there is no return current for positive and negative sequence currents. Okay. So for positive and negative sequence components, there is no return current. So that is the reason why we didn't include the neutral wire for drawing the positive and negative sequence network. Okay. So in the case of a symmetrical circuit. Coming to the zero sequence, they don't have any difference in phase angle. All the three, IA0, IB0, IC0 will be having same magnitude as well as same phase angle. So all three will be drawn in parallel. So there will be a return current in the case of a zero sequence component. So IA0 plus IB0 plus IC0 will not be equal to 0. So that return current should have a path. That is nothing but the neutral wire. So for this reason, we are drawing the neutral wire for zero sequence network. Okay. And we have seen in the case of zero sequence network, if neutral is kept ungrounded, we will leave that 3Z10 component open. Okay. So if the neutral is solidly grounded, so Z0, only Z0 will be present. Okay. So if we are grounding the neutral through an impedance, say Zn, so the total zero sequence impedance will be Z plus 3Zn. Z0 will be equal to Z plus 3Zn. This is what we have seen in the earlier classes. Okay. So now I will tell you why this neutral impedance is having a value 3Zn. Okay. So already we know the zero sequence current is not having any phase difference. Components is not having any phase difference. Okay. But the positive and negative sequence currents, they have the same 120 degree phase angle from each other. So because of this difference, the magnetic field due to the zero sequence current is different from the magnetic field caused due to positive or negative sequence current. Okay. So because of the phase angle concept, the magnetic field produced due to zero sequence current is different from the magnetic field produced by positive or negative sequence current. Okay. So due to this difference in the magnetic field, the zero sequence reactance or the zero sequence impedance is taken 2 to 3.5 times the positive sequence reactance. Okay. Okay. So for that is the reason why we are taking 3 into Z10. Okay. We are taking 3 into Z10 because of the difference in the magnetic field produced due to zero sequence components. Okay. So since a transposed transmission line is a symmetrical network, we take the sequence networks or similar to that of a symmetrical circuit. Okay, of a transmission line is same as that of a symmetrical circuit. So let us take Z1 as the positive sequence impedance of transmission line, Z2 negative sequence impedance, Z0 zero sequence impedance. Okay, so if you look on to the sequence networks, positive and negative sequence networks are drawn similar to that of a symmetrical circuit because a transposed transmission line is a symmetrical circuit. So VA1, IA1, positive sequence voltage and current, Z1 is the positive sequence impedance. VA2, IA2, negative sequence voltages and currents, Z2 is the negative sequence impedance. So coming to the zero sequence impedance, if the neutral is solidly grounded, there is no need to include the 3Z10. Okay. So Z0 represent only Z0 as the impedance. So if the neutral is grounded through Z10, So we take the total zero sequence impedances Z plus 3 Z10. Okay, so this is the sequence networks for a transmission line. Okay, so now let us look on to a few examples how to draw the positive sequence, negative and zero sequence networks for any given power system. So this is example 1. So what's given? Generator, motor. So between this generator and motor, this is the generating side, this is the load side. The load is the motor load. We have transformer, 3 transformers and 2 transmission line. Okay, so now in the previous classes we have discussed how to draw the sequence networks for a generator, for a transformer, for a transmission line. Okay, so motor is similar to generator except for the current direction will be changed. Okay, so here while drawing the positive and negative sequence network, there is no need to include the effect of neutral. Okay, so coming to the positive sequence network, see already you all are familiar with drawing the reactance diagram. So positive, negative and zero sequence networks are nothing but the reactance diagrams. Okay, so coming to the positive sequence network, so this part is for generator. So this is the positive sequence network for a generator. Okay, so Xg is the reactance of generator represented by G. This suffix 1 represents for positive sequence. Okay, and what is Eg? It is the EMF generated. Okay, it is the EMF generated. Okay, so don't bother about the neutral for drawing positive and negative sequence. Then what comes? We have a transformer. So transformer, how to represent? By the reactance of the positive sequence reactance, which is Xt1, 1. Transformer T2 is represented by reactance Xt2, 1. This is for transmission line. This is for transmission line 2. Again, this is for your transformer 3. And coming to this load side, it is a motor load, the winding reactance as well as the EMF. Okay, back EMF plus minus. Understood? So we are not considering about the neutral, or we are not bothered what is the connection configuration of the transformer also. Okay, transmission line is represented by a reactance. Transformer is also represented by a reactance, and generator represented by source in series with reactance. Motor also 1 voltage in series with a reactance. Since it is positive sequence diagram, you have to represent by the suffix 1. You have to represent by suffix 1. Okay. So coming to the negative sequence network. It is similar to that of positive sequence network except for the difference. Remove the voltage sources. And draw as such. Okay. So when you look on to this negative sequence network, the negative sequence reactance or impedance of the generator is taken as Xg2. Since it is negative sequence network, we are using the suffixes 2. For transformer, Xt1, 2, Xt2, 2. Transmission line, XTL1, 2, XTL2, 2. For the transformer 3, Xt3, 2. This is for the motor reactance. Okay. So what is the difference between positive and negative sequence network? So remove the or short the voltage sources, that is Eg and Em. Okay, that will not come in the negative sequence network. So coming to the zero sequence network, it is slightly different. Okay, so the transformer zero sequence network, the transformer reactance differs. It depends upon the connection configuration of the primary winding as well as the secondary winding, as well as the mode of grounding the neutral. Okay, so in the same way, generator neutral grounding also matters. Okay, so for this diagram, let's see how to draw the sequence zero sequence network. Okay, yeah, let us consider the generator. I think there is no doubt in drawing this Xg. reactance of the generator winding, represented by suffix 0, which represents zero sequence component. Okay. So now coming to the generator, it is grounded, the neutral is grounded through neutral impedance Zn. So what is the total zero sequence impedance of this generator? It is Xg0 plus 3Zn. Okay. Xg0 plus 3Zn. So this you should be careful. So in any given network, drawing of zero sequence network should be done with a great importance. Okay. Now coming to this transformer T1. So coming to transformer T1, what is it? It is a delta star. Okay. So how to draw delta and how to draw the star? In the previous lecture I have given different configurations for this transformer. Okay. So any transformer configuration, it has got a general circuit. Okay. So one reactance. Then on either sides it will be having series switches on, and it has two shunt switches also. Okay. So if the primary is star connected with the neutral grounded, you have to close the primary side series switch. Leave all the other three switches open. Similarly, if the secondary side is star connected, okay, with neutral grounded, you have to close the series switch on the secondary side. Leave all the other switches open. So if any one side is delta connected, you have to close the shunt switch corresponding to that side. Leave the other switches open. So now for this transformer T1, we have primary as delta and secondary as star without grounding. See, if you find a star with neutral not grounded, you have to leave that side series switch open only. Okay, you have to close the series switch only if you have a grounded neutral star connection. Okay, so now how many switches will be there? Primary side series switch, secondary side series switch. Primary side shunt switch, secondary side shunt switch. Okay, so what you have to do? You have to open the primary side series switch. You have to open the secondary side series switch. You have to close the primary side shunt switch. You have to open the secondary side shunt switch. Okay, so that is what I have drawn over here. So this is the transformer T1, which is connected between two terminals EF as shown in the given question. Okay, and we have taken a reference bus. Okay, so now primary side is delta connected, so I am leaving this series switch open. Secondary side ungrounded star, I am leaving it open, but primary side is delta, so I am closing the shunt switch. Shunt switch connect that particular side terminal with respect to the reference bus. Okay, so now coming to the transformer T2, what is it? Primary is delta, secondary is star grounded solidly. Okay, so what you have to close? You have to close the primary side shunt switch and secondary side series switch. Okay, see, secondary side series switch is closed, primary side shunt switch is closed, primary side series switch is left open. Okay, then coming to transmission line. Coming to the transmission line, it's shown by the reactance. Okay, same reactances I am showing here. Then coming to transformer T3. What about the primary? Grounded star. What about the secondary? Secondary is delta. So secondary side shunt switch to be closed, primary side series switch to be closed. Okay, so when you connect it, you will get like this. See, primary side series switch is closed, secondary side shunt switch is closed. Okay, secondary side series switch is left open because it is delta connected. Understood? Then coming to the motor. Motor reactance you represent xm, 0. Okay, and what about the configuration? It is star with neutral ungrounded. So if the neutral is ungrounded, what about Zn? Zn place you should leave it open. The Zn place is left open. Okay, so hope you all understood how to draw the zero sequence. So take some time, go through the previous lectures for drawing the zero sequence networks for all the components, for a transmission line, for a transmission line, for a generator or motor, as well as a transformer. Okay, so while drawing for transformer, we should be very, very careful. Okay, so the concept behind it is, see, I told you, in the case of delta, the zero sequence current IA naught plus IB naught plus IC naught will not be equal to 0. Okay, so whereas in the case of positive and negative sequence components, IA1 plus IB1 plus IC1 is equal to 0. Negative IA2 plus IB2 plus IC2 is equal to 0. So it don't want any return paths. Okay, so that is the reason why we are not considering the neutral wire for the positive and negative sequence network. So coming to the zero sequence network, since IA naught plus IB naught plus IC naught is not equal to 0, it requires a return path. Okay, so the return path is the neutral wire. Since the delta connection is not having a neutral wire, the zero sequence current will circulate within the delta and it will not come out of the delta. That is, for the lines connected to the delta, there will not be any zero sequence currents. Okay, and as I told in the transformer discussion, because of the transformer action, whenever there is a closed loop in the primary circuit, there will be current. Because of that current, a flux will be produced which links with the secondary, and secondary will have a current. Okay, so only if the secondary is closed, again a current will flow and induced EMF will be there in the primary and vice versa. Okay, so that is the reason why we should have a closed path or a continuity in the current only when there is a delta or a star with neutral grounded. So if there is no neutral grounding, there is no path for the current flow. So when you look on to this, see this star, secondary star connected, there is no neutral, no path, no closed path for the return current to flow. Okay, so that is the reason here there is open. Okay,